The Intermediate Value Theorem, IVT. Suppose that f of x is continuous on the closed interval a to b, and that k is any number between f of a and f of b. Then there exists some x value, we call it c, on the open interval a to b, such that f of c equals k. Let's draw a picture to start to see if we can begin to understand what that means. So I'm going to draw a continuous function f of x. When I'm doing examples, I like to do pictures or graphs that are not extremely complicated, but not overly simple either. It tends to help me understand what's going on. So I have a continuous function f, and I'll put down the interval a to b, like that. Now, we see up here that k is some number between f of a and f of b. So let's put f of a and f of b in our graph as well, like this. And then k is any y value between those two other y values. So I'll just pick a random one. I'll put it right there and call that k. And I'll go out to my graph and go down. Notice that this value is a y value, and there is some x value, we'll call it c, between a and b, such that f at c is equal to the y value k that we chose. So that's what the IVT is saying, but what does it really mean? Let's do a simple example. Let f be continuous on the closed interval 1 to 4. So I'll put 1, 2, 3, 4 like this. And we know that f of 1 equals 3, and that f of 4 equals -2. Is there an x value, which we call x equals c, such that f of c equals 1? That is, if I start at this y value and then go down to my final y value, and my function is continuous, does y have to equal 1 somewhere? Well, of course. So by IVT, we see that, yes, f of c, or y, equals 1 somewhere. Is there a c value such that y equals 0? Well, the same picture shows me, yeah, of course. So the idea is, if I start at a y value and end at another y value, and the function is continuous, then we must hit all y values in between those two y values. So is there a c value such that f of c equals 5? And the answer is maybe, because I don't really know how to draw the function. There's not enough information other than I start here and end down here. But what if f looked like this one? Then it is possible for there to be a y value, or a c value, I should say, such that the y equals 5. So our answer is maybe. So the IVT guarantees certain y values, but it cannot guarantee that it does not hit other y values. Looking at some counter examples, what if my function f is not continuous on the closed interval a to b? Does f take on all the values between f of a and f of b? So let's pick something like this. We'll call this a, and we'll call this f of a up here. And then I'll choose a b, and it's called f of b down here. If the function is not continuous, does y have to equal all the values between f of a and f of b? So when you're proving something is true, it must always be true. If it's true a million times and false once, we say that it is false. So to try to prove something is not true, we only need to come up with one counterexample. So what if I do a very simple graph like this? Where the function f is not continuous on the closed interval. Does y hit all y values between f of a and f of b? And the answer is no, of course it doesn't. Which is why the function must be continuous on the closed interval a to b. What if f is continuous on the open interval? Let's just look at what if it's continuous on the open interval only. Does it have to be continuous on the entire interval, including the endpoints? Well, let's see if we can come up with a counterexample to that. Let's call this f of a, and up here we'll put f of b. What if the function is continuous on the open interval? Must we hit all y values between f of a and f of b? And again, we're just looking for any counterexample, and I'll draw one for you. Notice that f of x is continuous on the open interval a to b, but the function does not hit all y values, not necessarily anyways, between f of a and f of b. Let's take a look at one advanced example, an application of the Intermediate Value Theorem. Let's prove that x equals cosine of x somewhere on the closed interval 0 to pi over 2. You may assume that both x, or any polynomial, and cosine of x or sine of x are continuous on any interval. Let's look at our proof down here. I'm going to start by defining a function f of x equals x minus cosine of x. And notice that if we can prove that f of x equals 0 somewhere, that's the same thing as proving x equals cosine of x. Convince yourself that is true, that if y equals 0, as we defined it, then x must equal cosine of x. So this is not that dissimilar from the problem we did up above, the numerical example. Let's find f of 0, which is one of my endpoints. Then f of 0 is 0 minus the cosine of 0, which is negative. And if we find f of pi over 2, which is pi over 2 minus the cosine of pi over 2, or 0, which is a positive value. So just a very quick sketch. My sketch isn't correct, but just to show what's going on, that if f of 0 is negative 1, and then f of pi over 2 somewhere over here is positive, say pi over 2, and the function is continuous, then clearly f of x must equal 0 somewhere. So by the IVT, f of x equals 0 somewhere. Notice that when we're proving this, I didn't ask you to find where f of x is 0 or where x equals cosine of x. I simply asked you to prove that it is a true statement somewhere.